In this experiment, I am going to do an oxidation of a molecule called 2-ethyl-1,3-hexanediol. That's this molecule right here. The oxidizing agent that I'm going to be using is just regular household bleach. The chemical formula for that is NaOCl, that's sodium hypochlorite. And I'll be using a catalyst, glacial acetic acid. Glacial acetic acid just means concentrated acetic acid. This just works as a nice catalyst. And the purpose of this experiment is to determine whether the household bleach is capable of oxidizing a secondary alcohol or a primary alcohol, or perhaps both. So we're going to be determining the structure of the product of this reaction and figuring out whether one or both of the OH groups was oxidized. So for example, perhaps only one of the OH groups gets oxidized, in which case this would give us this product right here, or maybe, again, maybe just one, but it's the terminal OH group, so that would give us this product right here, or maybe both of the OH groups get oxidized, and so that would give us this right here. We're trying to figure out if we make just one of these or if we make some combination of these three different possible products. And one of the tricky parts about this reaction is I'm literally using household bleach. It's kind of difficult to know the quantity of bleach that I need to use in order to get a complete oxidation of the starting diol. Partly because household bleach, the oxidizing agent does decompose over time, so unless I'm using a brand new fresh bottle, which I'm not in this case, the concentration of the sodium hypochlorite is a little bit decreased from whatever it may have been when the bottle was initially opened. Another problem that I encountered in this particular situation is that the concentration of the hypochlorite is actually not listed on the bottle. So I don't know if it's, let's say, 5% bleach or 6% bleach or something like that. So I'm going to be adding quite a bit of bleach. I'm going to be using about, I think, 35 milliliters. And then throughout the course of the experiment, every 10 minutes, I'm going to test the experiment to make sure that I still have plenty of bleach present. I'm going to be testing with starch-iodide paper, which I've used before. And if at any point during the experiment I find that I am running out of bleach, I'll just add a little bit more to make sure that I get a complete reaction. Let's watch. We're going to be starting with about 2.9 grams of 2-ethyl-1,3-hexanediol. It's a liquid, and I'm going to be putting it straight into this 125 milliliter Erlenmeyer flask. Feels like it's a really thick liquid because the pipette is having a hard time sucking up the liquid. .916. Here's the Erlenmeyer flask with our hexanediol. I'm going to add a stir bar so that this can just stir automatically. On the hot plate, I'll be using the stirring function but no heat. I'll be surrounding the Erlenmeyer flask with some ice. This is just for the initial part of the experiment where I'm going to be adding the oxidizing agent. This is just to help keep it from getting too hot. There's usually a little bit of heat generated when these reagents are initially added. So next up, I'm going to be adding the catalyst, glacial acetic acid. I'll be using this little plastic disposable pipette to add the glacial acetic acid. I only need 3 milliliters. Each one of these little plastic disposable pipettes is about 1 milliliter, so 3 squirts will be enough. It's important to note that these little disposable pipettes are not calibrated. They're not very accurate for measuring things out. But when we're just talking about a catalyst or, you know, a volume it's not important that we get it very accurate, this works just fine. Remember, there's a really small volume of the hexanediol inside this flask. The flask is actually really large considering the quantity of solution that's inside of it. So that's why you see me kind of rotating the pipette around as I'm squirting it in. I'm trying to mix the glacial acetic acid with the hexanediol. The last component that needs to be added is the Clorox bleach, which you can see there on the left-hand side. And I'm going to be adding the bleach through the separatory funnel. The bleach I want to be adding kind of slowly, so I don't want to pour it in all at once. Like drop by drop over several minutes is good. That'll help to control the temperature. So this Clorox bleach, as I said, it doesn't say exactly what the concentration is. So I'm going to be using about 35 milliliters. And then over the course of the reaction, I'll just keep monitoring the reaction to make sure that I still have some Clorox bleach present in the flask. If I don't, I can just add a little bit more. So what I'm going to do is adjust the stopcock on this separatory funnel so that the bleach gets added at a pretty slow rate. I'm going to try to not put too much of it in too quickly. Initially a little squirt there just to make sure that the stopcock is actually open. And I'm going to let that kind of stir and react and dissolve a little bit before I adjust it some more. Now what I want to do is I'm just trying to very slowly turn the stopcock until the bleach just barely starts dripping into the solution. I want a really small sized drip and a very slow drip. And once it starts dripping, I'm just going to let it just continue to drain. It'll take several minutes for all of the bleach to get added into this flask. And so we'll just let this drain out little by little. Now that the bleach has been added, I'm going to remove the separatory funnel and also remove the flask from the ice bath. And I'll let this stir at room temperature for about an hour. During that time, I'm going to be testing every 10 minutes to make sure that I still have bleach present. Put a little bit of solution on starch-iodide paper, and if I can see this dark blue-black color, then I know that I still have plenty of bleach. The reaction period is over now, and at no point during the reaction did I run out of bleach. So every time I tested with starch-iodide paper, I got a positive test. That means I still have some bleach present in this flask, and I need to neutralize it. The best reagent for neutralizing bleach is saturated sodium bisulfite. So I'm going to be adding this saturated sodium bisulfite until I get a negative starch-iodide test. At this point, what I'm trying to do is get rid of any excess unreacted bleach. I have absolutely no idea how much saturated sodium bisulfite this is going to take. So what I'm going to do is just add a squirt at a time and then test again. And what I'm looking for here is a negative test. So I want to see no sign of blue or purple or anything like that on the starch-iodide paper. And again, this is almost in a way more challenging than doing a similar type of thing with pH, because the starch-iodide paper just gives us a yes or a no. There isn't really indication of, how close we are getting to being done here. We just have to keep adding and testing and adding and testing. And sometimes it takes a lot and sometimes it doesn't take all that much. But you'll see when we get all the way done with this that when I test with starch-iodide paper, it looks just kind of white on the paper. Now that all the excess bleach has been neutralized, I'm going to neutralize the glacial acetic acid using 5% sodium hydroxide solution. Remember at the beginning of this reaction, I added 3 milliliters of glacial acetic acid. That was to serve as a catalyst. Now I want to get rid of that glacial acetic acid, and I'm going to do that by adding this strong base solution. 5% sodium hydroxide is not a very strong concentrated solution, so it's probably going to take quite a bit to neutralize the acetic acid. I'll be testing the solution using pH paper. I want to get the pH of the solution up high to around 11 or 12, which is going to be a dark blue color with this indicator. And I'm expecting that this is going to take quite a bit of sodium hydroxide. The concentration of this solution is a little bit lower than what I should be using for this process, but it's what I had available. And also glacial acetic acid, that means it's completely concentrated. So it's going to take quite a bit of sodium hydroxide to do this. But the reason I'm using, a kind of a gentle, sort of dilute sodium hydroxide solution is because I don't want to throw anything that's too intense into this flask and run the risk of damaging my product. So you'll see that this is going to take quite a few additions of sodium hydroxide. I'm going to get frustrated in the process and just start adding a lot at once, trying to get the pH up high. At this point, the reaction is complete. All of the excess bleach has been neutralized using sodium bisulfite. All of the excess glacial acetic acid has been neutralized using sodium hydroxide. And now what I have left is inside my Erlenmeyer flask, my product, and it is in water. All the water is there from the sodium bisulfite solution and from the sodium hydroxide solution. And then there's a lot of byproducts that are mixed in there as well. So my products with the byproducts. And all of it is aqueous. My product is soluble in ether, and so I'm going to try to extract or remove the product into an ether solvent. One of the challenges with this, though, is that my product is also soluble in water, so getting it out of the water and getting it into the ether is a little bit tricky. To help me accomplish this, I'm going to use a technique called salting out, which I have used before. For salting out, I'm just going to add a lot of sodium chloride, NaCl, into this flask. The sodium chloride is going to increase the polarity of the water, meaning that it's going to make it even more polar than water already is. And by increasing the polarity of the water, I'm going to make my product a little bit less soluble in water. So I'm going to make my water almost too polar for the product to stay dissolved. The product is going to stay dissolved, but it's just not really going to be happy about it. After I've added the NaCl, I'm going to transfer this whole entire flask into a separatory funnel. So it's all going to go into the separatory funnel, and then I'm going to add a little bit of the ether that I'm going to use to do the extraction. So the ether, which is lighter, is going to sit on top of the water. I'm going to shake everything up. The product is going to move up into the ether layer, and all of the byproducts are going to stay down in the water. Byproducts. I'm then going to remove the water layer and just kind of set it aside. And I'm also going to remove the ether layer and set it aside as well. The ether layer, which contains my product. After I've removed and separated the two layers from each other, I'm actually going to take this water layer and I'm going to put it right back into the separatory funnel. So I'm going to put the water layer back into that separatory funnel, this exact same water layer. And then I'm going to add a second round of ether. Shake it up again, and that is going to move any product that may not have moved the first time around. So any product that might have stayed in the water, hopefully now will get moved up into the ether. I'll drain that same water layer again. I'll drain this second ether layer and add it to my first, so they'll be all together like this. My ether and my product will be together. Once I've got them isolated and separated from the water, I'm going to take this, dry it out using some anhydrous sodium sulfate drying agent, and then I'm just going to let it sit overnight. The ether is going to evaporate from this because it evaporates very easily, and it'll leave behind my pure product. We're going to be using about 6 grams of sodium chloride for the separation and the extraction, which is a lot. .410. It's time for the extraction. I'm going to transfer the product into the separatory funnel. Right now this is just the water, the product, and all of the different byproducts. And now I'm adding the approximately 6 grams of sodium chloride into the separatory funnel. And again, the only solvent that's in here at this time is just the water. So right now what I'm doing is increasing the polarity of that water. I'm shaking this up just for the purpose of dissolving the sodium chloride. I'm not doing any kind of extraction technique right now. Still have to, constantly vent anyways. And so the sodium chloride has been mostly dissolved. It's a really saturated solution. And now it's time for me to actually do the extraction. So here I have diethyl ether, also known as just ether. I'm going to use about 20 milliliters of ether for the extraction. The hope here is that the product gets transferred into the ether layer because it's not really that soluble in water anymore now that I've added the sodium chloride. So this time as I'm shaking, this is actually hopefully an extraction. My product is hopefully moving out of the water layer into the ether layer. And I'm just going to let it sit, let the ether and the water kind of separate from each other. If you can see it's really hard to tell the difference between the ether layer and the aqueous layer, but that almost kind of cloudy stripe around the very top of the separatory funnel, that's the ether layer. With a little bit of time, it is going to clear up. That ether layer will clear up. And then once that layer is clear, I'm going to drain out and separate these two different layers. Now, if you recall, the strategy here is to drain the aqueous layer. The aqueous layer is the big layer that's down on the bottom. So I'm going to drain out the aqueous layer. And ultimately, I'm going to be putting that aqueous layer back into the separatory funnel to do another extraction. Just in case any of the product was left behind in the aqueous layer, I'm going to just repeat this whole entire process to try to get all of the product out of the aqueous layer. So right now I'm draining out the aqueous layer into this beaker. And as I'm doing this draining process, I want to get all of the aqueous layer removed, plus also a little teeny tiny bit of the ether layer drained out as well. My goal is that when I remove the ether layer from the separatory funnel, it's going to be just pure ether and product. There won't be any traces of water or byproduct or anything like that. So there's my aqueous layer. I'm going to set it aside, and now I'm draining out this ether layer. This ether layer contains the product. The ether layer is also going to get set aside. The aqueous layer going back into the separatory funnel again, and doing a second round of extraction with ether. Using, again, another 20-ish milliliters for this extraction, repeating the process. And just one more time, the goal here is to remove any product that may not have been transferred into the ether layer in the first round. So once these two layers have separated, and I can see like a clear division between the aqueous layer and the ether layer, once they have separated, I'm going to drain the aqueous layer, and it is going to get discarded. It's going to go into the waste container. The aqueous layer just contains byproducts, doesn't contain anything that's worthwhile. The ether layer that's in the separatory funnel right now is going to be combined with the very first ether layer that I removed. So the two ether layers will be put together. Doing extractions with ether and water is a little bit tricky because ether and water are kind of soluble with each other. And so when I get the two ether layers combined, I'm going to have to use a drying agent, this anhydrous sodium sulfate, that white solid that I just put down. I'm going to have to use that anhydrous sodium sulfate to help absorb any trace amounts of water that are in the ether layer. It's going to take quite a bit of the anhydrous sodium sulfate to completely dry, and again, that's just a characteristic of doing an extraction between ether and water. So knowing that I'm going to have to put quite a bit in, I'm just going to be, kind of pouring some in. Normally I would just use a scoop to do it, to just put a little bit in at a time. And what I'm looking for here is for all of the for the anhydrous sodium sulfate to stop clumping. I want to be able to pour some anhydrous sodium sulfate in and have it remain just granulated and not clump up. The portions of the anhydrous sodium sulfate that have already clumped will remain clumped, and what I'm looking for is the new stuff that I put in to not join in on the clumping. Once I get this completely dried out, then I am going to transfer just the liquid, leaving behind the anhydrous sodium sulfate. I'm going to transfer the liquid into an Erlenmeyer flask. Then I'm going to cover the top of the Erlenmeyer flask with a piece of lab film. It's kind of like saran wrap, and I'll poke some holes in it. That will allow for all of the ether solvent to evaporate, and it will leave behind just the pure product. I'm going to give it a few days to evaporate fully. So after a few days have passed, and the ether has evaporated, then we will characterize the product. This is the product from the oxidation of our insect repellent. It originally had ether in it, and I had it covered with some holes poked in that plastic for the ether to evaporate. So the ether's evaporated, and what we're going to do now is take a little sample of this and measure its IR. It literally just blew itself out of that pipette. This smells really strong. It smells pretty strong. So because it smells so strong, that means that it is really volatile. It evaporates really easy, and that's going to make it really hard to capture an IR. So what I'm trying to do is trap it underneath this tip, and then I want to get my spectrum as quick as possible. Ooh, it is a strong smell. Oh my gosh. Now, if I didn't get enough of the sample underneath there, or if it's evaporating too quickly, then what we're going to get is just really low transmittance. So the peaks will not be very strong. Remember, this comes in upside down. So kind of looks like that might be a carbonyl peak right there. All right, turn it around. It actually looks like the absorbance is not that bad. Initially it might look like it's, looks really good, but the scale right now is only going down to about 46% transmittance. So I can change the view to go from 0 to 100. But the peaks look pretty well defined. So I think that this is a good enough, at least it's good enough for us to work with. I'm gonna change the scale on this and then save a copy of it, and we'll use this to analyze the product.